Hi everyone, welcome to Chemistry Universe once again. I'm Kalyan Kumar and we'll be doing part 13 of the Alkyl Halide series. We are just near the end now. There is one more part after this and then this entire lesson will be over. In the last one, we talked about reactions of alkyl halides, and in this one, we're going to talk about preparation of alkyl halides. In general, whenever we do a functional group, we generally tend to do the preparation first and then the reactions. But in this one, we did a little sort of in the other way around. We did the reactions first and then we are doing preparation. And all of this is for a reason that, there are certain things which need to come first before you progress ahead. So it is keeping that in mind that I have deliberately done this. So let's move on to part 13 of the alkyl halide series, and this is the preparation, the various methods of preparation of alkyl halides. Some of them I'll discuss in detail in terms of mechanism. Some of them we're not going to discuss in detail. We'll be doing those in certain other lessons which will follow, like for example, hydrocarbons, etc. So that is what we're going to do now. So let's move on to part 13 of alkyl halides, that is preparation of alkyl halides. So here we go, part 13. So the first thing we're going to do is we're going to prepare alkyl halides by the reaction of alcohol and with HX. Now alcohols, when reacted with HCl, HBr or HI, produce the corresponding alkyl halide. And the overall reaction is ROH, the alcohol, and reacting with HX and you get RX. That makes sense. And let's see the mechanism. Now, I think the most obvious thing that you have understood right till now is that the alcohol would first get protonated by the H plus, and then it will become protonated alcohol. Now, in step 2, what happens to the protonated alcohol depends on the nature of R. If it is, if the R is tertiary or something that can produce a stable carbocation, it will go via SN1 to produce R plus. It will release water and produce R plus. Mechanism will be SN1. And then in the next step, X minus will attack and you will get Rx. Whereas if R were primary, which cannot undergo SN1, then what will happen is that it will happen via SN2. So what would happen is the X minus of the HX would attack the R with SN2 and simultaneously release water and you get Rx again. So the nature of the reaction depends on the nature of R. And as I said, methanol and primary alcohols react by SN2, while secondary and tertiary react by SN1 or SN2. I mean, secondary can do both and tertiary will preferably do only SN1. Now here you also need to understand that, we just saw ROH plus HX giving Rx and water. Sometimes they're not going to give the question that easily. They're not going to give you HX. They'll probably give you a combination of reagents that produce HX. So you may not see HX in the reactant and you'll start wondering what is happening. So you also need to know how HCl, HBr and HI can be produced so that in case they give you the reactants of these, then you know that, okay, if this is the reactant, HCl will be produced and ultimately it is HCl which is reacting. Or in this reaction, HI will be produced and ultimately it react with HI and I need to produce the product of that particular reaction. So we'll also see how these are produced individually. Okay, so HCl and HBr are produced by the following methods. You take NaCl and sulfuric acid and you will get HCl and Na2SO4. Again, you get HCl, that's the important part. Then again, if you take NaBr and sulfuric acid, well, it gives you sodium sulfate and HBr. But you cannot produce HI by this method. The reason you can't is because though HI will get produced, the HI produced, I minus is very easily oxidizable. And sulfuric acid is an oxidizing agent. So HI will react with sulfuric acid and get oxidized and end up becoming I2. So you won't get HI in a yield which can react further. So the best way to produce HI is by using H3PO4. You take NaCl, NaI and H3PO4, and here you get HI and Na3PO4. So if you are given reactants, instead of HCl, they give you a combination of this, you know HCl will be produced. If they give you a combination of this, you know HBr is being produced. And if they give you a combination of this, you know HI will not be produced, and I2 anyway is not going to react, so there will be no reaction. But if they give you this, you should know HI is being produced, and it is the HI which is reacting further. So let's move on. And now, since Cl minus is relatively a weaker nucleophile than Br minus and I minus, it needs a Lewis acid like zinc chloride to remove the leaving group in case of primary alcohols. Now, this is where you need to understand something, and that is that when a tertiary system is present in a protic solvent, which it is in this case, the solvent is water, and that protic solvent would enable the formation of carbocation, and the tertiary will react very fast. Primary, on the other hand, struggles even with SN2, because in the primary, what is happening is you have the nucleophile which has to attack first, and the leaving group has to leave simultaneously. So it takes greater time for SN2 to happen than SN1 to happen. Remember, primary doesn't promote SN2. It doesn't have anything to promote SN2. But primary is better for SN2 than secondary and tertiary because of less steric hindrance. So the absence of hindrance makes SN2 possible in primary. It doesn't make it possible in secondary and tertiary. So primary is not actually helping out SN2. It is not hindering it, which secondary and tertiary are. Whereas tertiary and secondary are promoting SN1 by hyperconjugation and inductive effect. So primaries will always react slowly. On top of that, you remember when we discussed nucleophilicity, I told you that as you go down the group, the nucleophilic ability increases. So Cl minus is better than F minus, Br minus is better than Cl minus, I minus is better than Br minus. So Cl minus being the weakest nucleophile in this case, the nucleophile is also weak and the reactant is also primary. So it becomes very difficult for the reaction to take place. So to help the reaction go reasonably faster, we use a Lewis acid like zinc chloride. And I'll show you how zinc chloride helps this reaction to go further. Okay. Now, other halides don't need the Lewis acid even with primary alcohols. Whereas secondary and tertiary alcohols don't need zinc chloride with HCl at all. So remember, secondary and tertiary don't need zinc chloride, only the primary does. And no other halide, whether it is primary, secondary or tertiary, needs zinc chloride. So the reactivity of HX is very simple based on the nucleophilic ability. And the reactivity of alcohol, as I said, SN1 is always faster. So tertiary, secondary, primary and methanol. Now here we talk about what is known as a Lucas test. So let me describe this test for you. In Lucas test, what we do is we use this ability, or rather the inability of the primary to react with HCl to form RCl. How we use this is, and of course, if you ever want the primary to form RCl by this method, by adding HCl, you have to add zinc chloride. And shortly I'll come to that part, how it does. So what we do is, let's say we have 3 test tubes and one has primary, the other is secondary, the third is tertiary, and we are supposed to find out which is what. So since we don't know which is primary and which is secondary and which is tertiary, we'll add zinc chloride in all of them and HCl in all of them. Solvent is water. Product will be RCl, no matter what kind of R you have. It may happen at different times, but all of them will form RCl. And RCl is insoluble in water, it will precipitate out. So when something precipitates out, it doesn't precipitate immediately. It will take a little time. The solution will become cloudy. It will become translucent, milky, and then slowly form a white precipitate. So the speed at which this precipitate is formed tells us what kind of an alcohol it is. And since you've already seen the reactivity of tertiary being more than secondary, secondary more than primary, So the immediate result, immediate cloudiness, immediate precipitate signifies tertiary. A little bit of more time, secondary, and a lot of time, primary. That is how this Lucas test works. So Lucas test is used to differentiate between primary, secondary, and tertiary alcohols. And Lucas reagent is cold concentrated, less than 10 degree HCl and anhydrous zinc chloride. Now, if zinc chloride is used, then secondary and tertiary alcohols react by SN1 while primary still reacts by SN2, which will be slow. Zinc chloride helps in making OH group a better leaving group than water. It helps in creating a carbocation faster, and I'll show you how that happens. When alcohols react with a mixture of zinc chloride and HCl, an alkyl halide is produced which is insoluble in water, which is the solvent. The alkyl halide form precipitates out. It first causes turbidity in the solution and slowly it precipitates. The rate at which turbidity is achieved is the measure of the test of the nature of alcohol, as I said in the beginning. So now let's see how zinc chloride helps. So you have a ROH, you have zinc chloride. The lone pair of O forms a coordinate bond with zinc because zinc chloride is Lewis acid, and you will get a compound like this, an intermediate like this rather. Now as you can see, this O plus has become a good leaving group, so this can very easily leave. So if it were tertiary, it will leave instantly. In secondary, it will take a little bit of more time because carbocation is a little less stable. With primary, it will only leave when X minus attacks. But this is a much better leaving group than simply OH2 plus, which is what would have happened had zinc chloride not been taken. So you have R plus formed, and then eventually the R plus will end up giving the Rx. Of course, with primary it will go by SN2, it won't give you Rx. So what is the rate? If you have tertiary, the turbidity is instant. With secondary, it takes around 5 to 10 minutes, and with primary, it takes 15 or sometimes even more than that. So now I want you to use this to find the answer to this particular question. The turbidity order of the following compounds when reacted with zinc chloride and HCl is. So you have to find out the turbidity order. I'm giving you 7 molecules. 1, 2, 3, 4, 5, 6 and 7. So let me number them. You have to find which will form turbidity fastest and slowest and write them in the decreasing order. And as is the practice, take your time, pause the video, do it on your own, and then play the video back to check your answer. Now, out of all this, which do you think can form the carbocation? Obviously, 1 can form, 5 can form, 6 can form, 7 can form. And out of these carbocations, which is the most stable one? It is number 7. Because if you remember, this is CPM. We've discussed that in GOC. It gives you cyclopropyl methyl carbocation, CPM. And that shows what is called as dancing resonance. And that makes it extremely stable. And therefore 7 is the best. Okay, 7 is the best. Which one do you think is next? Obviously between 5 and 1. And remember, we've already done 1 will be next because tertiary carbocation with 3 methyls is far more stable than a benzylic carbocation. And next, of course, will be benzylic because it has more resonating structure than 6. 6 would be there because it has 2 resonating structures. Then obviously we will have 2 because it has 6 hyperconjugations. Then you have 3 because you have 3 hyperconjugations. And in the end, you're going to have 4 because it will not have anything stabilizing the carbocation. In fact, it will go by SN2, which will be very slow. So this is the order. So take your time to understand this. The next thing we do is called the Finkelstein reaction. Now in this reaction, alkyl iodides are produced from other alkyl halides by reacting an alkyl chloride or bromide with sodium iodide in acetone. Now remember, if I take RBr and add NaI to it, and if the solvent were water, then I minus will replace Br minus because obviously I minus is a better nucleophile. But the difference between I minus and Br minus is not that high, so the reverse reaction will also happen. So this reaction is reversible in water, as iodide ion and bromide ion are both similar in their nucleophilic ability, of course not same, and as well as leaving group ability. So if I minus can replace Br minus, well, to some extent Br minus can also replace I minus. Now, but we want this in a major amount, which means we want this reaction to be unidirectional. And the way to do that is by changing the solvent. If I take the solvent as acetone, now acetone is less polar than water as well as aprotic. So what happens is that NaI and NaBr, if you compare these two, this is more ionic, whereas this is relatively covalent. That is because I minus is a bigger ion. It can be easily polarized compared to Br minus will be less polarized. Remember Fajan's rule? So based on that, this is more covalent. Bigger anions are more covalent than smaller anions if the cation is same. So in acetone, which is less polar, NaI is soluble, NaBr is not. So the moment the reaction forms NaBr, it will precipitate out. Now if this guy precipitates out, it will not remain in the solution. If it doesn't remain in the solution, there is no question of the reaction going backward. So it will be only forward reaction. And therefore, in acetone, NaI is soluble, while NaBr and NaCl are not soluble, as they are more ionic in nature than NaI because of higher polarizability of iodide ion. So what happens? Acetone is weakly polar, so it can dissolve more covalent NaI, but NaCl and NaBr need both cation and anion to be solvated for them to dissolve, and that is not going to happen in an aprotic solvent. Acetone being aprotic can only solvate the cation. So if you do the RBr with NaI in acetone, it will go unidirectional and form Ri and NaBr. Same is true for RCl. Now, acetone will only allow SN2 to happen. Meaning here the reactivity will be primary, secondary and tertiary. And the reaction is driven forward only because of the fact that NaCl and NaBr can be precipitated out. So reactivity is based on SN2 reactivity. And remember, only iodides can be prepared this way because sodium chloride and bromide are not soluble in water. So let's do a couple of examples and check. And remember, it is SN2, okay? So this is the first molecule, NaI acetone. I want you to pause the video now. Pause it, make the product on your own and then check. So let's see the solution. It's very simple. This is the place where the Cl is there. And since it is SN2, the I minus will come from the back side and Cl minus goes up. So this H ends up being going on top and the I is at the bottom. So you will get this. Okay. Go for the second one. Again, pause the video. So where is the leaving group? The leaving group is here. I minus will come from the back side and replace it. And remember, sometimes you may be given not exactly this. They may replace some, maybe they'll put the H here. Maybe they will put the H here and the Me here and stuff like that. So all you have to do is make even number of interchanges to see whether the molecule that you have got and they have given in the option are same or not. Even number of interchanges maintains the configuration. Odd number of interchanges would invert the configuration. And sometimes they can rotate this by 180 and give you the iodide at the bottom carbon. So don't worry, rotate it back by 180, bring the I up and then check whether the configurations are same or not while picking the options. Well, the next one, what do you think will happen here? Pause, make and play. And obviously I will come from the back side. So let's look at the fourth one. Try this and make the Fisher projection. Now, so what do you think will happen? Obviously, I minus comes from the bottom. So the best way to do this is either you make the reaction happen, then make the Fisher, or make the Fisher first and then see the reaction. So what I'm going to do is I'm going to make the fissure first. So what I'll do is let me bring, let's say, the D up, or I'll just draw the fissure like this, okay? I'll draw the fissure like this. The Me is at the bottom. Now here I have to bring something at the bottom, so let me bring the D at the bottom. So bring the D here at the bottom, Cl will go right, H will go left. And here I've put the Me at the bottom, so D is on the right, H is on the left. So I minus comes, attacks this carbon, Cl goes. There's an inversion of configuration and I get Me here, D here, H here, I here, H here and D here. Let's see what they have made. Now you want to check whether this is the answer or not? Well, they have put the D on top. So make changes on this carbon to bring D on top, but make two interchanges to keep the configuration same. So first I'll interchange D and Me. Then I'll change Me and H. Don't you think I'll get this one only? And the bottom one remains as it is. So what we have made and what has been made here is same. Question 5. Now what do you think will happen here? Be very careful in this. You're likely to make a mistake. So pause the video, make the product and play the video back. Now here, even though you would expect the I minus to come from the back and remove the Br, the product is this. There is retention. Because what you might have missed is that this nitrogen has a lone pair and it can show NGP, neighboring group participation. It will attack this carbon and the Br will leave. So it will form a 3-membered ring with nitrogen, NH2 positive. Then the I minus has to come only from this side to break the NH2 bond and you will get this. Remember, they could have made the I minus attack this carbon also and made the product. And they might have ended up making both the products. So you'll have to check for both of them whenever NGP occurs. So along with this, you will get this also. Because remember, the I minus could have attacked this carbon also because it has already formed a ring now. So now these two carbons are similar. So if it were to attack this carbon, the I will go here. If it goes to this carbon, the I will go here. Go for the next one. Try this. Pause the video. Now you might feel again NGP happening, right? But no. Remember, in NGP, you'll always find SN2. This carbon has tertiary butyl group at the adjacent carbon. It is so hindered that SN2 simply cannot happen. And the carbocation of this is extremely unstable. It has got only one H for hyperconjugation. No hydrogens beneath. So carbocation cannot form, and as it is, acetone will not give you SN1. You can only do SN2, and with a hindered system, SN2 simply will not happen and you will have no reaction happening. Alright, so far we have seen chlorides, bromides, iodides being made. Now let's look at something that can produce fluorides. And this is the only reaction to prepare alkyl fluorides. Now an alkyl chloride or bromide is reacted with fluoride of a heavy metal like mercury, silver or antimony, whose chlorides and bromides are insoluble as they are more covalent. Now what you need to understand here is this is the reverse of Finkelstein. In Finkelstein what happened was the solvent was less polar. So the more covalent NaI dissolved and the more ionic NaBr, NaCl didn't. Here the solvent is water and we are taking heavy metal halides. So heavy metal fluoride are ionic because less polarizability. Whereas heavy metal chlorides and bromides are covalent. And water being polar solvent, it will dissolve the heavy metal fluoride but will not dissolve the heavy metal chloride or bromide because they are relatively less ionic and more covalent because of polarizability of the anion. And therefore what will happen is that as the heavy metal chloride is formed in the product, it will precipitate out. As the heavy metal iodide is being formed, it will precipitate out. So this is one of the best and probably the only method for producing fluorides from chlorides and bromides of alkyl halides. And the solvent taken is polar protic solvent, water. Okay, so here we go. A polar protic solvent like water is used as solvent. And you have this, even though I'm showing you this, but it will be preferred if I were to take a tertiary one because it is water and go by SN1 and Hg2F2, and this gives you the fluorine product, and it will give you Hg2Cl2, which is insoluble in water because of more covalent nature and precipitates out. The same is true if you take AgF. You can take cobalt, you can take any transition metal, heavy metal halide. But you cannot take NaF or Kf because NaCl and KCl or NaBr and KBr formed will also be soluble in water. So you cannot take the alkali metal halides. The next is called the Borodine Hunsdiecker reaction, made by three people, Borodine and a husband-wife couple, Hunsdiecker. Now here what we do is we take the silver salt of an aliphatic or aromatic carboxylic acid with Br2 or Cl2 to produce alkyl halide. So basic reaction is you have silver salt of carboxylic acid reacted with bromine. The solvent is a non-polar solvent, and which sort of implies that it could be some kind of a free radical mechanism. And it gives you RBr and you have CO2 and AgBr. Now you have to remember the reaction, okay? So you have to ensure that you remember the reaction because that will help you form the products quickly. But at the same time, you also need to know the mechanism because there are some questions which can only be done by mechanism. Now this is a free radical reaction, which is why we need a non-polar solvent. And what is the driving force? The driving force is the formation of CO2 gas that escapes and AgBr where that forms a precipitate. And the mechanism is pretty simple. We first take carboxylic acid and add moist Ag2O. And if you remember from the previous video, moist Ag2O is nothing but AgOH. And that will react with this to give you the silver salt. Now this silver salt reacts with a bromine molecule. And first the O minus of the RCO minus will attack the bromine and Br minus will leave, giving you RQBr and AgBr, forming a precipitate, which is what drives the reaction forward. Now, since it's the free radical one, we have the chain initiation step where the RQBr would break homolytically. The OBr bond breaks homolytically and you get RQ dot and Br dot. This is the chain initiation step. Now, in the chain propagation step, the RQ dot would rearrange to form R dot and CO2 gas, which again drives the reaction forward. Now it is all about the reactivity of R dot. Now this R dot will pick up the bromine atom, form RBr and get back the carboxylate radical. Now what you need to understand in this kind of reaction is that, as I said, it's a free radical reaction. And in the initiation step, you will get two radicals or two atoms or an atom and a radical. In the propagation step, you will get that there will be generally two steps. And the two steps will be such that in the second step, you will get the product that you desire as well as the radical that is consumed in the first propagation step. So the reaction can keep propagating. Let me help you this with a small example. So what happens is, let's say there are 100 molecules. There are, let's say, 10,000 molecules of this in the beginning. And let's assume only 10 molecules of this break because all of this break by heat or sunlight. So I only give sufficient heat or sunlight to break 10 molecules. So I'll get 10 of this and 10 of this. Now 10 of this will completely become 10 of this and 10 of this. That is because CO2 is being liberated, so the reaction goes forward. Now the 10R dot, with whom does it have a greater chance to react? Obviously with 10,000 molecules of RQBr. Remember, we have got 10,000 molecules of RQBr and 10,000 molecules of Br2. So all of them are forming this. So RQBr is 10,000 now. So 10,000 of this out of which 10 reacted to form 10 and 10. This 10 gave this 10. Now this 10 has a higher chance of reacting with this because the amount of this left is 9,990 because only 10 have reacted. So the chance of R dot meeting this is far greater than even RQ dot. So R dot meets this, you get RQ dot and RBR. This is the product we desire. Now can you see that whatever RQ dot got consumed in the first propagation step is being produced in the second one? So the reaction keeps going. 10 will react again 10 will react. It will keep on happening till such a time when RQBR is reduced to as small a value as, let's say, 10 or 20. In which instance, or rather at which instance, you will find the chain termination step happening where radicals end up meeting each other. Radicals and atoms meet each other. Even the atoms can meet each other, or you can have different radicals meeting this. And ultimately what will happen is the reaction will stop, and that happens only near the end of the reaction. Now again, if you were to go back to the previous one, let's try and see if we can go back. Okay, we've gone back. Now if you notice, R dot is produced because of CO2 gas being released. That makes it irreversible. So it doesn't matter whether R dot is stable or not. If R dot is tertiary or primary or secondary, it will form anyway because of the CO2 being released. But this reactivity of R dot is what defines how fast the reaction is going to go. Therefore, what do you think will be the reactivity of R dot? Don't you think primary being less stable will be more reactive? So ease of formation of Rx is methyl X, primary, secondary and tertiary. So let's do a couple of examples. The first example is a very simple one. Make the product. So remember the final product of the reaction, RQAG gives RBR. So you will get this. What do you think will happen here? Same option, pH, Br. Now what do you think will happen in this one? Now this is where the mechanism comes into play. Now you might be tempted. In making Br here and Br here. But no. Remember, it goes through free radical. So you will get a free radical here. And after this QAG goes, you will get a free radical here. What do you think will happen? The two radicals will meet and it will give you alkene instead. The next is reaction of PCl3 and PCl5. Now with PCl3 is pretty simple. You take alcohol, you'll take PCl3, all the Cls will replace the OH. So there are 3 OH and there are 3 PCl3s. So you'll get 3 RCls and you'll get H3PO3. And the same thing will happen with PCl5. The difference being that only one ROH reacts with one PCl5. The Cl, one Cl will go with R, one Cl will go with H, and the O will be taken up by the P, and you will get RCl, POCl3 and HCl. So let's first see the mechanism of PCl3. So you have alcohol and PCl3. O having a lone pair acts as a nucleophile on phosphorus. Cl leaves. So Cl minus is leaving and you will end up getting something like this. And as you see, O plus is formed. Good leaving group. So the Cl minus that left will attack the R, SN2, and this will break and you will get RCl and there will be one OH on P. Now it has got 2 more Cls left. So you will have 2 more alcohols it can react with. They also will have their OH replaced by Cl just like this one. So you will get 2 RCl and again you will get 2 more OH. So P ends up having 3 OH. Now technically this is H3PO3, but H3PO3 doesn't actually exist like this. H3PO3, what it does is because of the d orbital of phosphorus, you will have a back bonding. So it will exist in this state. More covalent bonds, more stable. But this will show tautomerism. And the H will end up going to phosphorus. And you get this. And the mechanism, as I said, is SN2. So there will be complete inversion of configuration. and the rate is obviously based on SN2. Now PCl3 and PBr3, remember, are formed by the reaction of red phosphorus with X2 because PX3 is not stable and has to be prepared in C2. So PCl3 and PBr3 again are prepared in C2 because they cannot be prepared in CAPT, number one. Number two, even white phosphorus can give you PCl3 and PBr3, though we use red phosphorus because white phosphorus is unstable in air. It will readily combust at around 30 degrees Celsius violently, extremely exothermic. So we don't use white phosphorus. Red phosphorus reacts slowly, so we tend to use red phosphorus for this reaction. Now comes the mechanism with PX5. Now this is pretty interesting. You have PCl5. So you have PCl5 reacting with alcohol. The O will attack the P and the Cl will leave, and you will get something like this. Now the Cl minus bond will take the revenge on R, attack R, and this will break, and you will get RCl and you will get a OH instead of a Cl. Now what happens is that this lone pair comes and attacks the P and the Cl leaves like a nucleophilic substitution, and you will get double bond OH plus, and the Cl minus will now take the H plus and form HCl and POCl3. Okay, now you also need to understand one more thing. And this is for PCl5. PCl5 will react with many compounds containing oxygen, not just alcohols. What it does, it will break the O is always bonded by two bonds, right? It will break both the bonds. And if the two bonds are made with different atoms, it will give one Cl to each atom and take the O and form POCl3. So PCl5 will lose 2 Cl per PCl5, one to one of the atom forming the R attached to O, and the other Cl to the other atom attached to O, and then it will take the O as POCl3. If there's a double bond, it will break both the bonds and give 2 Cls to that atom because the double bond is with one atom. But it prefers to break the single bond first rather than the double bond first. Now, why am I saying this? Because it will react with acids, esters, anhydride, many compounds, but it will not react with acid chloride. So, if acid chloride is ever formed, it will remain as it is. So, PCl5 also reacts with other oxygen-containing compounds like aldehydes, ketones, carboxylic acids, ethers, esters, anhydrides, blah, blah, blah. It does not react with acid halides, however. And PCl5 converts all the oxygen bonds with Cl and gives as many Cl as the number of oxygen bonds broken. It takes the oxygen to form POCl3, and PCl5 prefers to break singly bonded oxygens first compared to doubly bonded oxygen atoms. So let's check out this with a couple of examples. So the first one coming up is alcohol with PCl5, which we have already done. I think this is pretty simple. Remember, it will break two bonds of the O, one with the R, one with the H, give them both Cl and form POCl3. Try this, pause the video, make the products, then play the video back. So can you see it is attached with two bonds to two different R's? It gives Cl to both and forms POCl3. So you get this. What do you think will happen with aldehyde? Pause the video. Now there is no single bond O, there's a double bond O. It will break that and form two Cls and form POCl3. What do you think will happen with a ketone? Same logic, both O's broken, two Cls and POCl3. What do you think will happen with carboxylic acid? Now here, there's a double bond O as well as a single bond O, right? Double bond O, single bond O. Which one does it break first? Singly bonded oxygen first. So first, let's break this. So it will break the two bonds of the OH on carbon and H. What will you get? You'll get RCOCl and HCl and POCl3. Now it will not react further with this. This is the only thing it does not react with, acid halide. Alright, next one. You have a diether Obviously, you require 2 PCl5. Pause the video, make the product, play the video back. Obviously, it will break these two, it will break these two, and you'll get Cl everywhere and 2 POCl3s. Anhydride, which will it break? Single bond or double bond? Obviously, single bond first. So it will break this, give 2 Cls, both of them will become acid chlorides. They won't react further and you'll get a POCl3. Try this with an ester and see what happens. Again, 2 single bonds broken first, acid chloride, R prime Cl, POCl3. What do you think will happen to this? This is cyclic ether, epoxide. Again, both single bonds get broken, 2 Cls and POCl3. So now let's do something like halogenation of alkanes now. Now this again is something which you might have already done in hydrocarbons when you were in grade 11. But anyway, now here any alkane with a Cl2 with H nu and heat, you will get the alkyl halide and HCl. And remember, out of all the methods of preparing RCl, this is probably the worst. Because the problem is you do not know whether you'll get a monochloro derivative, you'll get a dichloro derivative or a trichloro, you'll get all the mixtures. So it's very difficult to curtail the reaction to only one of them. You know, if you take excess of the alkane, even there you cannot say which H will go more. So again, you will get a variety of products. So if at all you are ever asked a question, which is the worst possible way of preparing an alkyl halide, it is this one. But it does produce an alkyl halide, which is why we are discussing it. Okay, so here we go. We have alkanes can be halogenated by treating them with halogen molecule in the presence of heat or ultraviolet light. And for gaseous alkanes, this reaction is carried out in the gaseous state. And for liquid and solid, it is done in CCl4, which is of course a non-polar solvent. Now let's quickly look at the mechanism. The chain initiation step, chlorine breaks into chlorine atom. The propagation step, the alkane takes one of the chlorine atoms and it gives an H, forms a methyl radical and you get HCl. The methyl radical on the other hand will react with a chlorine molecule and you will get chloroethane and you'll get a Cl dot. That's how it propagates. The Cl dot is consumed, formed, keeps on going till in the end the atoms end up meeting. The atoms meet radicals, radicals meet radicals, and you will get a variety of terminal products. And there are a couple of more details in this that we'll discuss in the case of alkanes. When we do the lesson alkanes, we'll discuss more details of this. The next is, of course, treating the alkenes with HX. So alkenes can be halogenated by treating them with an HX molecule. It is addition reaction. So you have an alkene, you have HCl, you have a protic solvent. Now the alkene would take the H plus first and one of the carbons will become CH3, the other will become the CH2 plus, and that will take the Cl minus and you'll get alkyl halide. So mechanism goes like this. The alkene always loves an electrophile because remember it's an electron rich pi electron cloud, electron rich molecule. Now the pi bond can move to one of these carbon atoms and that takes the proton and that becomes CH3, the other becomes carbocation. Obviously I could have chosen a better substrate to give the carbocation a little more stability, but anyway I'm taking this to make it simple. Then you have Cl minus attacking and you'll get this. And again, there are a couple of more details and which we'll do in alkenes. Then comes halogenation of alkenes. Now by halogenation of alkenes, what we mean is that we are going to add a Cl2 or a Br2 molecule to an alkene. So the alkene having a double bond, the pi bond breaks and you will get 1,1 Br on each carbon or 1,1 Cl on each carbon. So that is halogenation of alkenes. So alkenes can be converted to vicinal dihalogen compounds by reacting them with a molecule of halogen in a non-polar medium such as CCl4 or CS2. So we have alkene reacting with Cl2. We take a non-polar solvent, and why we take a non-polar solvent, etc., we'll discuss later on when we do alkene specifically. Though the solvent is non-polar, the mechanism is ionic in this case, and the alkene is able to polarize the halogen. So this is because the alkenes are highly electron rich because of the pi electron cloud and can polarize a neutral molecule like X2 by, it's not inductomeric, actually it is electromeric. This should be electromeric effect. Okay. So Cl2 breaks into Cl plus and Cl minus. In fact, it is the alkene which breaks this. Then the alkene will take the electrophile because of the electron richness that we discussed before. And now you get a carbocation. The other Cl minus will attack this carbocation and you will get two halogens attached. Okay. So the important thing that you need to know in this is that if you look at the step where the halogen is breaking into Cl plus and Cl minus, it is equilibrium, right? So to make the reaction go completely forward, we take excess of halogen. More halogen, Le-Chatelet principle says more forward. Second thing is two molecules are combining into one, alkene plus Cl2 giving a vicinal dihalide. If two molecules are becoming one, entropy is decreasing. And if entropy is decreasing, delta S is negative, and already there is a negative T delta S. If delta S is negative, it will give a plus D delta S. So delta G to be made negative, the temperature must be low so that the T delta S value does not dominate the delta H value. Now delta H value will be negative, otherwise delta G can never be negative. But if the T delta S value is low, then the delta H numerical value can dominate. So we will do the reaction at high concentration of Cl2 and low temperature. Okay, so this reaction proceeds to give a good yield if the concentration of X2 is high, which tends to drive the forward reaction, the first reaction forward. Moreover, since two molecules are combining into one, the entropy is decreasing, so the reaction is favorable only at low temperatures, and further details again will be done in alkenes. And then we do perhaps the last reaction of this video, and that is halogenation of allylic and benzylic carbon. Now the allylic carbon in alkenes or the benzylic carbon in aryl systems can be selectively halogenated by treating them with a molecule of halogen in the presence of heat or sunlight. Now remember, what is allylic carbon? It is attached to the vinylic carbon, remember? This is allylic carbon. Now we can selectively halogenate this, or for that matter, benzylic carbon. We can selectively halogenate this carbon because they are very much prone to having this reaction done because their radicals are pretty stable. Again, it's a free radical mechanism. You need sunlight or heat, and you will get the allylic halogenated product, and the H that comes out of the allyl carbon forms HCl. So the reaction again proceeds through free radical. Again, you have the chain initiation step. Then you have the propagation step. In the propagation step, if the Cl dot were given an option, it will only take the allylic H to form the allyl radical, which is resonance stabilized. Remember, resonance stabilization. Then the allyl radical will react with the Cl2, giving back the Cl dot and take the Cl on the allylic carbon. And this reaction will keep on going. Termination steps. As you know, the radicals meet, radicals and atoms meet, and the reaction gets terminated. Now you have to understand that this reaction competes with addition of alkene. Now if you remember, in the addition of alkene, addition of halogen to alkene, we use a non-polar solvent, CCl4. Why? We'll discuss later on. But we do use that. So if we do use that, and this is also happening in a non-polar solvent because of free radical mechanism. So this will compete with addition. But what did we use to make addition happen more? We took halogen concentration high, temperature low. We'll reverse this. We'll take low halogen concentration and high temperature to avoid addition and make allylic halogenation possible. So to favor allylic halogenation, we keep the concentration of halogen low and the temperature high. And one of the best methods of doing allylic halogenation is simply by using NBS or NCS, which is N-bromosuccinamide or N-chlorosuccinamide. That is this. So this is a very good reagent for doing allylic halogenation. Now the way it happens is NBS first reacts with trace amount of water to form HBr. So there is a little water and the little amount of NBS will react with a little amount of water to form a little amount of this compound and HBr. A little amount of this would rapidly react with the HBr formed. In fact, the NBS left will react rapidly with the HBr, which is little of course, to form this one and form Br2. So obviously when this is trace, remember this is trace, and if this is trace, this is also trace. So Br2 automatically comes up in low amount. And a slight amount of heating will produce the radical and make the reaction of allylic halogenation possible. Now there is one more thing that you have to understand. When you are doing questions of allylic halogenation, don't just make the halogen on that carbon which is allylic. Meaning, of course, you got to do that, but you also have to see its resonating structure. Because it is allylic, it will resonate with the double bond. So you have to make the halogen happen on the other allylic carbon also after resonance. So you have to make all products like that. And if there are multiple allylic carbons, you have to make multiple products as long as they're all different. And you will understand this with the help of some of the examples I'm going to show you now. Okay. So example 1, try this. Tell me how many products do you get? How many structural isomers do you get? How many total compounds do you get? So pause the video, make all of it, and then play it back. So here is the solution. The first allylic carbon I can notice is this one, right? So the H of this will go and the Br will come here. Now, I'm also going to make its resonating structure. So this unpaired electron will come here. One unpaired electron from here will go here. And this will become a radical. So don't you think you'll get the Br here also? Okay. Now, this is another allylic carbon. So can't you get a Br there? And this will also undergo resonance. And when it does resonance, you'll get the dot here. Now you will notice this product and this product are same. So if I ask you how many products you will get, you might end up, you'll be tempted to say 3. Because this of course is similar to this. But remember, when somebody asks you the number of isomers, you must include stereoisomers as well. Now look at this carbon. Isn't it chiral? So won't you get R and S? So 2 of them. Can you see in this is chiral? 2 more. Can you see these both are chiral? 4 more. And this of course is same. So how much do you get actually? You get 8 products. But 3 of them are structural isomers. Right? Okay. So try making it with this. And remember, be very careful when you make it with benzylic, because in benzylic, you should keep the product aromatic. The benzene ring should not become non-aromatic at the end. That product won't be stable. So in showing resonance with benzylic, don't make the halogen on the benzene ring, because that will lose the aromatic character. So you have to do whatever resonance you do outside, but it will undergo benzylic halogenation. Okay. So which are the allylic carbons? There is one allylic carbon, one benzylic carbon here. Can you see there is a one benzylic carbon here? And if someone were to ask you total number of structural isomers, obviously 2. Total number of isomers, this carbon is chiral. 2. This is chiral and this is chiral. So 4. So here you get 6 products, 2 structural isomers. Try this one. NBS. Now, let's start. Let's start with this one. Allylic carbon. Can you see this will resonate? and you get the radical here. Okay. Now let's check out this radical and its resonating structure. And then you have this radical and its resonating structure. And you will notice that we've already made this. In fact, this and this are same. You check this out. If you don't understand whether they're same, just do the IUPAC nomenclature and you'll get the same name for all of them. But there is two of them. So how many structural isomers? Obviously 5. Total isomers. Well, there is no chiral carbon here. So this is 1. This carbon is chiral. So 2. This carbon is chiral. So 2 more. This carbon is chiral. 2 more. This carbon is chiral and 2 more. So that makes it 9. 9 total compounds. And that ends this particular video, part 13. So I hope this video helped you in understanding the preparation of alkenes. Go through this video as many times as you want. If you have any questions, any suggestions, please drop them in the comment section below. And I'll catch you in the next video, which will be the last part of alkyl halides, and that is polyhalides. And I'm going to try and make them as fast as possible so that we can wrap up this topic. With that, this is Kalyan Kumar signing off. Have a great and wonderful day, and thank you for watching this.